Welcome back to Demystify Sci. Today we have a real treat for you. We have Simon Michaux from the Geological Survey of Finland. And Simon has a very, very interesting take on the energy landscape of the future. Not necessarily a critical one, although we do spend a bit of time deconstructing and renumerating all of the different issues with our present fuel economy. But he actually has a solution set that doesn't involve humans bad, we're all screwed mentality that we come across so often. He's actually got a four-part plan for how we're going to deal with the internal combustion engine, how we're going to deal with readily available and wasteless nuclear power. And the list goes on and on. So this is a conversation that I honestly couldn't be more excited about sharing because it's one of the first times that somebody's really put a salient solution set on the table that makes sense to me, and I hope it makes sense to you.
Simon's whole point is that right now most of the conversations are about the green transition, and the green transition is structured mainly on the back of wind and solar. And if you do the calculation of how many resources you need for wind and solar, just on the foundation of copper, nickel, lithium, cobalt, you really quickly discover that in order to really create systems that have uninterrupted power supplies that can operate year round, you need like 4 times more raw materials than there are thought to be on Earth, period.
Green on it. There you go.
Yes, no, we'll wait. We'll wait till she comes back.
Eh, you can
Or do
go
we just
ahead.
go?
Yeah.
All right,
Uh,
go. So this is what I presented in Australia recently. And so the questions I asked was, what's required to phase out fossil fuels? How big's the existing system? What do fossil fuels do for us? What are the primary tasks of the green transition? And then wind and solar, what do they need? What's the quantity of metal needed to construct a complete system that completely replaces everything? And can recycling supply this quantity, and can mining supply this quantity? And if that won't work, what will? And this is where we're leading to what we call the purple transition. So I asked the basic question, will the green transition work for all of us the way we think? Well, how do we continue to resource this? So there are 3 maps. So this is the first map of the work done, where on the left we've got the fossil fuels, then the major tasks. Then if we were to knock them out and replace them with different things that are not fossil fuels, how do we get to the end? So what were the physical tasks in 2018? What was the true scope of work done? Useful work. Assemble a series of non-fossil fuel systems like wind turbines, solar panels, batteries, what have you, to do the same thing. Calculate the extra electrical power needed. And then using an energy mix proposed by the IEA for 2050, how many new stations will we need? Like how many solar panels are we going to need to do this? And so on. So, and the elephant in the room was the power buffer for wind and solar is actually much larger than we think. And that is a problem. And until we solve that problem, wind and solar are not viable as the primary energy solution going forward. They're a support system.
You make this case about the power buffer, which is that wind sometimes goes away for weeks at a time and it's spread out through an entire region. So if the
Yeah.
UK is wind powered and the winds die in the UK, it's entirely possible that the winds also die in Germany and
Yes.
France and Belgium all at the same time. And so these countries can't trade grid backup between each other. And so instead of having 6 or 7 hours of buffer, you were talking about needing like 2 to 4 weeks of buffer.
Yeah, and in fact, the real number could be closer to 12 weeks. And so,
It's a lot of
yeah,
buffer.
so this is the problem. So 1.4 billion vehicles traveled 16 trillion kilometers in 2018. We need something like an extra 50,000 terawatt hours of power, which is like 800,000 new power stations. Put this in context, in 2018, we produced and consumed 26,652 terawatt hours. So it's, roughly half that. And the power plant fleet was 46,423. So we're talking about more than 10 times the power stations to do this. And this is, if we took out a single coal-fired power station, how many solar panels do we need to replace it? That's what that is. So this is an audit of an energy grid in America called PJM RTO. They manage like 100 million people. And so this is like a full year audit for wind and solar. And this was, and then you get onto the website and download this information. And so what I found was that wind and solar underperform for 4 to 6 months of the year consistently. Like for several months in a row, things were a problem. Like we were below par, and they were at different times, like seasonally different times. Like winter, when you really want to spend a lot of power heating buildings, you've got very poor solar performance. And so this suggests the idea that conventional thinking that 6 or 7 hours is enough to balance the difference between winter and summer is ridiculous. So so here's like a case study in Spain of concentrated solar power for June and November, like summer and winter. If this was a standalone system, it would be 670 megawatts, and you would need the dark orange things on the graph here is from storage. So for the month of November alone, they would need 16 days of buffer capacity, and they'd need to store it for about 4 to 6 months. Right. So this is the.
It's a lot of flywheels.
Right. So yeah, well, flywheels have their place. They all have their place. But we don't have the ability to store such a lot of power for such a long period of time. Like, can you have a flywheel spinning and keep that power for 6 months and come back in 6 months and have that power still accessible? Right. So the second system, now that we know how much extra power we need, how many physical units, how much steel, hydrogen, ammonia production annually, what's the metal content of each wind turbine and solar panel and what have you, what battery capacity needs to be operating, what is the market share of the different battery chemistries that's possibly going to happen in 2050, and what's the metal content of each chemistry. So that gets us to the total metal quantity required. And so when we got that, how do we get it? So now we know how much metal. So where do we get it from? Can recycling deliver? And can the existing mining industry deliver? The answer is no. Can we expand quickly, like falling back on mineral reserves? Or can we, for example, look at mine resources? Or here's a really dumb idea: can we mine the seafloor? Or do we consider developing a fundamentally different plan? And that's actually the answer. So where this goes.
Why is the seafloor dumb, by the way? We had a lady a long time ago present a really interesting plan for just scooping up these balls of metal that are
the polymetallic nodules. But I think
so the metal is
Simon
down there,
makes the point that it's not enough.
The metal is down there. We don't know enough about enough metal, but to mine something like, enough of that order to deliver, say, 20 million tons of copper a year to the market. Think of the sediment pollution that would then impact the ocean and what that would do to what's left of the wildlife down there. That's the problem.
Gotcha.
The environmental impact of mining. You can mine in a small volume in a boutique fashion, but now start pulling 3,000 tons an hour off one site.
That's pretty much the rest of the fish gone.
Right. So what you're looking at here is the numbers for there's 4 buffer sizes for wind and solar. 6 hours is what the conventional thinking believes, all the way out to 12 weeks. So 6 hours, 48 hours, 28 days, and 12 weeks. Then you got on the left-hand side the mining production of the global mining industry in 2019, the last year before COVID, the last year of sensible data. So let's pull out copper. How many years of production do we need to actually hit to produce enough copper to build the buffer? So if it's 6 hours, that's about 12 years. That we could do. But if the real number is between 28 days, which is 254 years, or 12 weeks, which is 745 years, right? The scale of the problem is unprecedented. And we want to get it done in 25 years, by 2050. Right, so let's look at thorium first. Thorium molten salt reactors in a modular form. So this is the, what you're seeing here is the title page of a report from 1972 of the Oakland Ridge Nuclear Laboratory, basically a status report of several decades of research saying that molten salt technology for generation of nuclear power works. Now, what this is, a normal reactor has got like solid fuel and rods and they insert it into a environment, and they bombard it with neutrons, and that heats water, and that water turns to steam. You've got like fissile uranium. This is thorium and a little bit of uranium in a salt form. They bombard that with neutrons from a neutron source. The neutrons convert or transmute some of that thorium into a fissile uranium isotope called U-233 that heats it up. The heat melts the salt and it starts to flow like a liquid. That liquid then moves around a heat exchanger, and heat is transferred to another heat exchanger, which then turns water into steam. That steam turns a generator generates electricity. So you've got molten fuel that's then kept hot by the decay of uranium inside the reactor. The fuel you put in is thorium-based, and it's not radioactive. It's what's called fertile, so it's not as dangerous to handle. Because it's already molten, you can't have the reactor melting down. Because of a phenomenon called Doppler broadening, this reaction, if it gets too hot, it will cascade and collapse in on itself. Right, so it can't actually sort of run out of control and have like a Chernobyl or a Fukushima system. You've also got the concept of a freeze plug, where if it gets too hot, then the fuel just drains out of the reactor and can be managed safely in a series of small contained units. Fuel, it's what's called neutron absorbing, or the colloquial term is poison. It actually absorbs neutrons and actually disrupts the reaction, can be taken out while the reactor's running. And fresh fuel can be added again while the reactor's running. So this is a small system. It's fundamentally different from conventional nuclear, almost to the point where it should be called something else. Here is the Oakland Ridge salt reactor from 1969. It ran for 6,000 hours without a problem. It proved it worked. In China at the moment, there is a system that's actually running, and it's actually commercially selling power. It's only 2 megawatts. But the Chinese and in fact, all BRICS countries are actually looking at this very carefully. Once they actually sort of put it through its paces, I think they're going to mass produce these. So let's look at the difference between the different nuclear systems. 1 gram of uranium or thorium of the right isotope can produce 24 megawatt hours of thermal energy. Let's start with uranium. We are going to mine 156,000 tons of ore and make, through conversion and then enrichment, 36.9 tons of uranium fuel rods. Now, most uranium is uranium-238. That isotope is not useful in maintaining a nuclear chain reaction. You need uranium-235. You've got to enrich that, because most uranium is only like at 0.7%. So you've got to enrich it to the point where it's useful. That's the enrichment process. It needs about 4%. You put it into a nuclear reactor and you run it for 365 days. You generate 10,000 gigawatt hours of electricity, and 96% of those fuel rods come out as waste. So you end up with about 31 tons of waste, and that is mostly uranium-238. Why? Because it's uranium-235 that generates the reaction. Right, let's do the same thing now, but with a thorium MSR. We're now going to mine 290 tons of monazite sand. So already the front end of this sequence is several orders of magnitude smaller. From that, we're going to make about 1.3 tons of thorium fluoride salt. It's like a combination of things. It's a small amount of uranium, a bit of beryllium, a bit of lithium-7, all that. You put it in the reactor. You generate 10,000 gigawatt hours of electricity, and about 3% of that fuel is not consumed in the radioactive transmutation cycle. It's about 48 kilograms. So 48 kilograms versus 31 tons. So each one of these systems produces 100 megawatts of thermal heat, or about 40 megawatts of electricity. Here, they load 50 years of fuel at commissioning. And every 5 years, they'd come back and actually sort of, strip out all the, in a maintenance cycle, there'll be parts that are actually decayed through, a lot of the steel parts will be decayed through, neutron degradation. A small system. So every industrial site, like a smelter, for example, can have one of these on site. So we leave it in there long enough, uranium-238 would then actually go through several decay steps to get to uranium-233, and that is the fissile fuel that runs the MSR. So what that means is spent nuclear fuel can be consumed in an MSR in small quantities. So this is actually a solution for the stockpile of spent nuclear fuel. Right, now let's get down to the comparisons. Right, so here you have on a graph, to generate 1 gigawatt of electricity, we've got 14.8 tons of uranium mined, or 0.089 tons of thorium. We've got to put in a mineral processing plant to prepare the fuel 27.88 kilograms of uranium for the system, or 170 grams of thorium. The amount of fuel that is consumed, like the massive reactor fuel, we've got 3.13 kilograms. What's those two together? Like about 3.26 kilograms versus 1.32 kilograms of thorium.
0.132.
The amount of waste produced. So what we're saying here is the amount of waste produced by the thorium system is several orders of magnitude less than what's coming out of the uranium system. Now, to answer your question that you had before, is this table here. Okay. All right. So what you've got here, if we looked at uranium, and if we were to actually consume 29,165 terawatts of electricity, and that is actually the most recent consumption of energy, electrical energy, that we've actually consuming on a yearly basis. Right. So, but if all of that came from uranium, it would have our existing resources and reserves that we know of would last 29 years. If we were to do the same thing, but all of our energy came from thorium in an MSR, all of that resources that we know of at the moment would last 1,306 years. To go again, if we were to combine uranium and thorium together in the most efficient combinations, and if we were to include the spent nuclear stockpile, all of that together input in an MSR system would last 6,260 years. If you look at that table that's on the screen at the moment, the spent nuclear stockpile would buy us 78 years at current consumption on its own. Right? That is something like 2.5 times what the current uranium resources would give us.
And you think the primary pushback to this comes from the extant nuclear industry?
That's interesting. So when I was looking into this, I asked the basic question, why is it that if thorium was so great, how come we haven't heard about it? Right. In 1972, when that Oakland Ridge report was released, they were at the decision point. Now, at the time, they didn't have an energy crisis. They didn't have a resource crisis. They didn't even have an environmental crisis. What they had was the Cold War. And at the time, the US military in particular were calling the shots. And what they wanted was a uranium-based civilian nuclear power plant fleet that could be used to camouflage the production of nuclear weapons.